Okay, super. Okay, thank you for the opportunity to talk about this work. This is work that I released in January, and as it says here, the title is Ultraviolet Finite Resummation of Perturbative Quantum Gravity, and you'll see what this means as we go along. So, as everyone knows, quantum gravity is not perturbatively renormalizable. Working in Euclidean signature so that we can properly analyze the divergences. The Einstein-Hilbert action takes this form. The natural coupling constant here is kappa, which is just 1 over the Planck mass. And that's your first clue, as again, everyone knows that this is a non-renormalizable, perturbatively non-renormalizable theory. You've got this negative dimension coupling. And another clue is if we say for expand around flat background with this fluctuation field here defined, H, then what you end up with is an infinite series of couplings. Sorry, an infinite series of operators. And when you compute loop diagrams, you'll find that you get divergences, new divergences at each loop order. And they require counter terms, which introduce new couplings. And so you end up with an infinite number of new couplings through these loop corrections. So this, of course, is the standard story as to why gravity is perturbatively non-renormalizable. But on the other hand, gravity has another problem, which is that in Euclidean signature, this action is unbounded from below. So if you follow the signs through, the problem is in the large positive curvature manifolds. And it means that this partition function expression here does not even naively converge, as these authors discussed back in the 1970s. So if we're going to make sense out of quantum gravity, it must be that this thing can be suitably reinterpreted. And I want to argue that if you do so, it might even solve the first problem, and in fact, make the theory finite. So the problem can be seen in to sit in the so-called conformal factor degree of freedom. It's the trace degree of freedom at this perturbative level. It's the overall size of the metric. And in fact, I'm going to parameterize the metric in this way. So I have an exponential of the conformal factor with coefficients with such that it matches this to first order. And then the functional behavior with respect to the traceless part is just subsumed in this G hat, and I won't need to specify it. So if you make this substitution into the action, then this is what you get. And I want to draw your attention to this exponential, which, therefore is parameterizing the overall size of the Einstein-Hilbert term, and is a positive exponential of the conformal factor for all dimensions greater than 2. And the other thing that's interesting is that you generate a kind of kinetic term for the conformal factor, and it comes with the wrong sign in dimensions greater than 2. So actually what I'll need is just 2 key properties. First of all, the interaction terms have got to be all contain positive exponentials of the conformal factor. And secondly, I need the conformal factor to propagate with the wrong sign. Now, this is kind of natural, given that you've just seen that it has a negative kinetic term. But actually, to answer that properly, you need to gauge fix. So that's the next step that I want to do. So here again is the parameterization of the metric and what the Einstein-Hilbert action looks like. And to gauge fix, we need to add a term like this. I've got here the square of the gauge fixing functional, a gauge parameter alpha, and this is the ghost action, which is given by the anti-ghost times the BRST transformation of the gauge fixing functional. And the gauge fixing functional I'm going to choose is one which is basically de Donde gauge, that you would be used to seeing it look like so, but I'm going to make it de Donde gauge using the full metric. So it's equal to the standard gauge fixing choice up to some interaction terms, in fact, infinite number of interaction terms, which is this order kappa part. Okay, so if you substitute this parametrization for the metric, it takes this form. And you see that you've got a positive exponential. So I need those two key properties. One of them is that all the interactions have a positive exponential of this conformal factor. And you see that the gauge fixing functional does through this choice of gauge. And if we do the BRS transformation of the gauge fixing functional, well, we just need the BRS transformation of the metric. That goes via the Lie derivative in the usual way. And you see, again, this BRS transformation has a positive exponential of the conformal factor. So putting those bits together, these interactions, which take into account the gauge fixing and the ghosts, also have this positive exponential. Well, now we can answer the question about whether phi propagates with the wrong sign. And the answer is, it does for certain gauges. So this is what phi propagator looks like in momentum space. And so providing you choose gauge alpha, which is outside this finite range, then phi propagates with the wrong sign. It propagates with a minus sign here, this bit being larger than this. And in particular, that includes the case that the interesting case is, for example, it includes the case d equals 4, which is the physical dimension, and the popular Feynman-de Donde gauge alpha equals 2, where h mu nu and phi decouple. You can see that alpha equals 2 would cross this piece out. But leaves you with a phi propagator that propagates the wrong sign. Okay, so the next step is I want to preserve these exponentials of the conformal factor. They will be important. So I'm not going to expand in the usual perturbative way. I'll split off the kinetic terms, which will give us the propagators. And in effect, I can just treat the rest of the action, the interaction part of the action, as a single vertex. So I'll introduce a counting parameter, epsilon, which will organize this resummed perturbation series. Of course, epsilon really is 1, so later on we'll acknowledge that. But for the moment, I just introduce this epsilon and use this as its counting parameter. So what you do is, for example, for the Einstein-Hilbert action, here again is the vertex that I'll use. But because we've taken out the bilinear terms, I need to subtract from this all the bilinear terms that are sitting inside this vertex. And I do the same for the ghosts and the gauge fixing part. Now, the action is linear in this fake coupling epsilon, but when I get to the Legendre effective action, its interactions will be a series in this epsilon. And you can work out that series and find closed form expressions for these gamma n using flow equation techniques, essentially. I'll just show you the answer. You can understand this answer pretty well just by thinking about the statistics of Feynman diagrams. So algebraically, they can be expressed in terms of exponentials of this operator here that I called curly Pij. So what is this? This is contains the propagators and functional derivatives with respect to the fields, which act only on the ith or jth copy of the actions used. So you'll understand how it goes in a second. At the lowest order, the first order, what I get is this first order piece of the Legendre effective action, and it's the exponential of this operator acting on the interaction term from the effective action. And in this case, the functional derivatives just act on this action functional. So if I expand this exponential, it's just a series of propagators being attached to this action. It just gives this set of tadpole corrections. So that's what you expect, right? Because I'm just keeping one power of the interaction vertex, but I'm working out the quantum corrections to all orders. And so it can't be anything but a set of tadpole corrections. So that's what the first order piece looks like. The second order piece, the algebraic expression looks as follows. So you have an exponential now of this operator where one functional derivative acts on one copy of gamma 1 and the other functional derivative acts on the second copy of gamma 1. And what this does, if you expand it out in a power series, is it just attaches propagators between the two vertices. So you get, this is just the exponential expanded out essentially. Second order, third order, fourth order. The first two orders are missing because of this subtraction term. And what this subtraction term does is just basically take into account the fact that this is meant to be the Legendre effective action. So it's the generator of one particle irreducible diagrams. So you have to subtract the disconnected piece and the one particle reducible piece. This piece would just draw a propagator, single propagator between the two interactions. So that's your second order piece. And we can go on and write out the third order. The third order algebraically takes this form. But again, it's easier to understand what this means if you think about the diagrams as being created. So what you get is a linear topology. You've now got three vertices. And you have this linear topology where you connect these vertices by a sum over these Malonic expansions here and here. And so that's this piece here, except for subtracting the bits that are disconnected or just one particle reducible. And then you have this triangle topology where you can connect these vertices via a sum over a Malonic expansion for each pair. And you just have to remember to subtract the disconnected pieces in this case. So something I should have said is I should have explained from a diagrammatic point of view why you end up with this, say, at second order. So at first order, I'd already explained that you've just got one vertex. This black dot here is the classical interaction, and you just have summing over tadpole corrections. So at second order, you're going to have two of these SI vertices. So that's your two vertices here, more or less. And then you've got to attach propagators in all possible ways. So that then sums over all the quantum corrections. And one way that you can attach propagators in all possible ways is just to keep adding tadpole interactions, tadpole corrections to these vertices. And what that does is it just turns this classical action vertex into the into gamma 1, the first order piece. So that's why, in fact, gamma 1 appears here and not S. So that just subsumes all of these tadpole corrections to these vertices. And then you're just left with the possibility of attaching one vertex to another via any number of propagators, and that's this Malonic expansion. So in a similar way, you can see that the answer has to be this if you think about the statistics of just forming Feynman diagrams with to all orders with only 3 interactions. And here in the left-hand corner is what it looks like at fourth order. So I won't have a lot more to say about that, but basically the pattern continues. Okay, so now let's have a closer look at the first order. So here it is again. It's a sum over all the tadpole corrections. But in quantum gravity, these tadpole corrections are all massless tadpoles. So what the strategy is going to be to first sum over all the conformal factor corrections. But these are massless tadpoles to the conformal factor. And if we use a gauge invariant regulator like dimensional regularization, then massless tadpoles are just set to 0. So that does nothing. Then we have to add in all the other corrections, which involve ghosts and h mu nu. But they're also massless tadpoles. And so if we use dimensional regularization, for example, then they also vanish. And so actually, trivially, gamma 1 is just equal to the first order piece of the Legendre. Effective action in this way of resumming things is just, again, the classical interaction. Things get more interesting at second order. So here again is what the second order thing looks like. And we're going to sum over the conformal factor corrections first. So first thing to note is that the first order piece is just the classical action, remember, and it takes the following form. So most importantly, the interactions all have this exponential, the conformal factor, with some positive coefficient, which is encoded in this beta alpha. So this is the thing that was d-2 for the Einstein-Hilbert action. And then you have some Lagrangian density factor, and it depends upon the conformal factor and derivatives of the conformal factor, space-time derivatives. And I'm suppressing for the moment its dependence from all the other fields. And then remember, we have to subtract the bilinear terms because they were all piled into the propagator pieces. Okay, well, the first thing you notice is that in analyzing this, is that we can ignore this 1 and this P12 piece. Remember, this just gives a disconnected contribution. So that's obviously UV finite. And this just gives you the one particle reducible contribution, which is also obviously ultraviolet finite. So to just analyze whether the overall ultraviolet finiteness, we can ignore these two pieces. So that's written on the next transparency. So that's why I've crossed them out here. And actually, then you notice you can also ignore the bilinear piece. And that's because supposing we use this piece in one of these diagrams, for example, well, then that's just going to give 0 because there are only 2 fields in here, but we need to attach at least 3 propagators. So that does not contribute to all of these. It can only contribute to this. And if we use a bilinear piece, say here, well, then that just removes this vertex. So we just end up with a tadpole, massless tadpole contribution, which again is 0. So from the point of view of analyzing the ultraviolet finiteness, we can ignore these annoying little pieces. And we're left with the second order contribution being the exponential of this operator acting on these gamma 1s, and with gamma 1 taking this form. Okay, so to compute this exponential, it's very useful, well, in fact, essential really, to go into position space, because then, you know, if we're doing this in momentum space, I'd have to think about my momentum routing and it would get complicated. But in position space, all I've got here is a series of propagators which are being multiplied together. So a propagator at x starts at x, finishes at y, say. And so this has got 2 of them, this has got 3 of them multiplied together and so on. That's just this exponential. So let's write everything in position space. And the crucial propagator I want to think about is that of conformal factor. So it's just the scalar, standard canonical scalar propagator times a negative coefficient. So this chi-squared here is just the gauge parameter dependent piece. And I'm choosing a gauge such that this is chi-squared is positive, so that this is overall negative. So the standard scalar propagator looks like such. It's got a bunch of numbers, not very interesting, in d greater than 2, and it goes like 1 over a power of x. So in particular, in 4 dimensions, this is 1 over x squared. Okay, well, we can sum over all of those propagators by using a trick which is, you will recognize as basically the kind of trick that you use in functional analysis. I'm going to introduce a source term, j, in the exponential that multiplies the exponential of phi piece that I know all of these interactions have, and then differentiate with respect to the source to bring down phi into the Lagrangian density factor. And finally, then I set j equal to 0. And if I do that, then actually this exponential of this operator only acts on this exponential of phi. And what does it do? Well, you know, exponentials have the unique property that you differentiate them and the same after you've differentiated them. The only thing you do is you bring down the coefficient in front. And so these derivatives with respect to the field phi will just bring down these coefficients. And so I can resum over this full melonic expansion, and what I get is this expression here. So here are the Lagrangian density factors waiting for their derivatives to be performed. This e to the p hat piece here is the attachment of all the propagators from all the rest of the fields. But for the phi propagators, the full expression is given in here. So here are, again, the exponential of phi pieces that belong to each of these sources, to each of these vertices. And then this piece here is just the result of replacing these functional derivatives by these factors here. So it has this square form with delta playing the sitting in between. Now, the crucial thing is that in here we have e to the minus chi squared, kappa squared, product of these two positive factors beta, and this propagator delta. And because of this minus sign, it has the following effect. As we bring the positions x1 and x2 close to each other, that's where we get our ultraviolet divergences from. This comes from the fact that the propagator tends to infinity as we bring these two pieces together. But because I've got this overall exponential factor, actually what happens is it now tends to zero exponentially fast. And it's a fact that e to the minus delta goes to zero faster than any power of delta or any power of 1 over x. So instead of actually getting UV divergences now, everything tends to zero as you try and bring these positions close to each other. So the thing is UV regularized. And furthermore, if we now consider doing the rest of the quantum corrections, if we handle those perturbatively, we start adding graviton corrections using HBU nu, for example, that just brings extra powers of delta in front here. But this exponential, it dies sufficiently fast that nevertheless, as you bring x1 and x2 close to each other, the whole thing vanishes. So no matter how many propagators you involve with the gravitons or the ghosts. So you can see order by order now, everything is UV finite. So just to be completely explicit, here's an example where I've taken the Einstein-Hilbert vertex and computed the remaining functional derivatives encoded in those source derivatives. And this is what you get. So it's a bit of a mess, but the crucial point is that you've got this exponential of minus delta up here doing the UV regularization. And then along here, you've got various field-dependent pieces, which, if you expanded in perturbatively would give you the vertices at gamma 2 for any number of legs, and various factors of propagators and differentials of propagators. But these propagators and differentials of propagators, although they diverge as you bring x and y close to each other, they diverge, this thing dies faster. And so the whole thing is UV regularized. Okay, well, now it's a question of checking that this works beyond just the second order. And it does. So here's the third order case again. And you see that the point is that if you actually compute these Feynman diagrams and sum over the phi corrections, you're going to get an exponential factor, again, where this is positive. This is your propagator, which is doing the phi propagation, and it's been resummed into this exponential, and this gives you the UV regularizations. So in principle, we would have, for example, in this linear topology, UV divergences if this vertex tends towards this vertex. So if x1, say, tends towards x2, But it's completely regularized by this thing where I put xi equals x1 and xj equals x2. Similarly here, I could get UV divergences if this pair of vertices come together, but it's regularized by this melonic expansion, which resums into this exponential. You could worry about these two vertices coming together, x1 and x3, say, but there are no propagators joining directly x1 and x3, and so there's no UV divergences to worry about. So this is completely regularized. And the same goes for this triangle topology, similar arguments. Now, any pair of these vertices can come towards each other, and you see that they're regularized by this melonic expansion that sits between them. And in fact, you can send all three vertices towards each other, but they're simultaneously regularized by all three of these melonic expansions. Now, I've left out some wrinkles, but to be complete, let's think about the wrinkles. The wrinkles come from these correction terms that give you the subtract the one particle reducible and disconnected pieces, and also from the bilinear pieces that I need to subtract from the vertices. So first of all, what about these subtractions? Well, it's kind of similar argument to before. For example, supposing I look at this piece. This piece subtracts the case where these two are disconnected. So between where the vertex 1 and 2 are disconnected. But if you subtract that, then you see what you're left with is just the melonic expansion we had at second order, which we already know is UV finite, times a disconnected piece that can't give you an extra UV divergence. And the same goes for this one particle reducible piece. That would just have put a single propagator between these two, but that doesn't give you any UV divergences. And so that case is just exactly the second order case that we've already analyzed. And if we look at the triangle case, well, it's kind of similar story. Again, we have to subtract the disconnected pieces. But if I think of this disconnected piece, for example, so I just remove this term, then you see that what I'm left with is the linear topology, which we've already shown is UV finite. So that story continues, basically. The more complicated topologies, all of these correction terms are already justified by the less complicated topologies. That leaves the bilinear terms to worry about. But if we pick, say, a bilinear term from this gamma 1 vertex in the linear topology, well, I can't do that in the center because I need 4 propagators coming from it, and I don't have enough fields for that. I could put a bilinear term at either end, but that would then turn this thing into a massless tadpole again, and that vanishes, so I don't need to worry about them there. Here, there's one case that you might worry about, which is where you pick a bilinear term for just one of these vertices. Then you get this diagram. However, this is just 2 propagators chained onto each other. So that goes like 1 over x to the 4th. This is no longer UV divergent. Well, actually, it would be, under some circumstances, it would be logarithmically divergent. But we don't need to worry because it's fully regularized by this melonic expansion here. And the final wrinkle is to think about the other fields. So now on top of this, we then build perturbatively all the corrections to the other fields. And I need to convince you that all of those are still UV finite. And the one exception is the case where, say, for example, you attach a ghost propagator from through these 2 outer vertices like this. Because there's no melonic expansion to directly regulate it, so you might worry that this is actually UV divergent. But then you realize that the combinatorics is such that actually it's this melonic expansion here that's regulating this. This is the case where you have 0 propagators, conformal field propagators going from this term to this term. But then you add in all the other cases, the 1 propagator piece, which is where this starts, 2 propagators and so on, and you sum over those, and that gives you this exponential factor, which actually regularizes this. So everything works. You can now do all the other quantum corrections, and they'll all be regularized by this conformal factor melonic expansion thing, which gives you this exponential suppression. Well, so far I've talked just about pure quantum gravity. Now let's talk about, and the Einstein-Hilbert action. Now let's talk about other possibilities. So the easiest one to discuss first is the cosmological constant. We can add a cosmological constant term, and because it's got a positive exponential of phi, everything just goes through as before. That's the one key property I needed. The phi propagator still propagates with the wrong sign, and so we're done. The scalar fields, again, all we need to do is to check that there are positive exponentials of phi, and that's true for both the kinetic term and for the interactions. Fermions, again, it's true. This is the spin connection, and if you count up the powers of phi in here, they cancel. Vector fields, at first sight, cause you a problem, because vector fields would give you this factor in the exponential, and in the physically interesting case of 4 dimensions, that would not give us a positive exponential of phi. But we can easily fix that by, for example, making the contravariant vector the fundamental field. So that actually what goes into the Lagrangian is this expression. And then you get more than enough positive exponentials of phi from this translation here when you substitute it into here. The one case where you can't just directly use the interaction is the so-called Starobinsky term, the square of the scalar curvature, which is a physically allowed correction to Einstein gravity, and indeed is one of the leading contenders for explaining inflation. But although we can't use the Starobinsky term because we don't get a positive exponential of phi, and here we don't have the wriggle room to redefine anything, we can just use the correct inflaton potential to reproduce this in the Einstein frame. So it's no big restriction. But there is one wrinkle if we now introduce massive fields. So, for example, massive matter fields. And that is that at first order, we're going to get massive tadpoles. And massive tadpole diagrams don't vanish, and they're furthermore divergent. However, we can discard all of those quite trivially. For example, by using the rather ancient these days system of normal ordering the vertices. So that then just automatically sets these all to 0. So these divergences are kind of trivial. They redefine the couplings in the action, but they don't do so through any momentum-dependent vertices, so which is why you can just redefine your couplings and forget about it. Okay, but it's not all sweetness and light. There is a severe problem with this procedure, and that is in diffeomorphism invariance and BRST invariance. And to explain that, what I need to do, what's the easiest way to do this is as follows. And that's to think about how you would set up the same framework, but now expanding around a non-trivial background and using manifest background covariance. So these propagators now are going to be, I'm going to consider the case where these propagators are just the inverse of the background covariant Laplacian. So they contain the background field inside them in such a way that this is now a covariant expression, diffeomorphism covariant. Background diffeomorphism covariant, to be precise. Well, now where's the problem? Well, the problem is, let's now go back to the first order, gamma 1. So it is a sum over tadpoles. The simplest case is this tadpole. And this tadpole I just set to 0 because in dimensional regularization, that's what it is. But now this is propagating in a background, and the background dependence is inside this propagator. So we can expand perturbatively in the background, and we can see that we can spit off any number of legs to the background fluctuation field. So this is no longer just a simple integral over 1 over p squared, which is 0 in dimensional regularization, but actually hides many interactions, infinitely many interactions. For example, at the simplest level, I can pull out a background leg from the vertex here, and I can pull out a background leg directly from the propagator, because this thing depends upon the background. And you see that this is a self-energy term, which is momentum dependent. You definitely can't just set this to 0. But then if you think about it, you realize that that interaction must already be in the theory. I haven't been throwing away any interactions. And it's inside this first term of the melonic expansion. So if I just took off a background leg here and here, I could reproduce this exactly. So that tells you actually that the melonic expansion, if we add all the other propagator terms in, must regularize this. So that makes it sound like we've succeeded. But now we need to think about how this thing transforms under diffeomorphism invariance. And you realize that, well, first of all, these vertices here, these gamma 1 vertices themselves contain tadpole corrections, and those tadpole corrections we can't throw away anymore. So here's a tadpole correction with a background dependent piece leg pulled out, for example. So we're getting vertices which are divergent, which look like this now. And that needs regularizing. And you realize, well, yes, again, same argument. Those interactions are already included, but they're included in the linear topology at second order. But if we include this, we need to include all its propagators, and so on. So I gave one further example, which is that I pull out a background dependent piece on one of the propagators and form this thing here. And you realize that this is actually regularized by the triangle topology at second order. And following that argument through, you realize that you basically need to sum over all of the gamma n before you have a hope of getting background diffeomorphism invariance. So that actually brings me to the summary of my talk. So what you've seen is that we can resum quantum corrections into a series of UV finite gamma n. And this works also for matter fields, providing we delete the tadpole corrections, for example, by using normal ordered vertices. But the problem is that we've seen that for background diffeomorphism invariance, we would need to somehow resum over these gamma n, and I don't know how to do that. And in fact, we're kind of hobbled because there's no small parameter anymore over which we can resum, because we've already done a non-perturbative summation over kappa, and this epsilon was really a fake parameter. It's equal to 1. I haven't shown you that the same is true for BRST invariance. The argument's a little bit more complicated, but it goes through. You can show that BRST invariance can be expressed in terms of things very much like the gamma n that I've just showed you. But in order to recover BRST invariance, we would have to sum over all of these guys. So what have we got? Well, we've got a series of, by reorganizing the perturbation series, we've got something which is UV finite order by order in these gamma n. But now we have to remember, we have to be a bit more mathematical about this. And now we have to remember that what a perturbation series is it's not even, it's certainly not absolutely convergent perturbation series. It's not even conditionally convergent. It probably isn't even Borel summable, for those who know about this. So it's a rather badly behaved series. So in mathematics, you can show, and you probably remember this from your undergraduate lectures, if a series is only conditionally convergent, then it is possible to get different answers by rearranging the terms. And we're certainly rearranging the terms here on a series that's even more poorly behaved. But you can take the view that, well, that's fine, but nobody knows how to define quantum gravity, or for that matter, quantum field theory beyond a certain few examples. And so we can just say, well, I define my quantum gravity to be this series. Well, that would be great if these guys actually satisfied all the properties we know we want them to, but we've just seen that they don't. So at this point, you kind of reach an impasse, and I can't push it any further. Is this just random that we can resum it into a sort of UV finite terms? Or can somebody do better and push this a bit further and solve these problems? I just don't know. And at that point, I finish the talk. Thank you.
Thank you, Tim. Let's all thank Tim. On my side, specifically for the nice summary and outlook. I think that's very helpful. I'll ask for questions and meanwhile stop the recording.